Welcome to Unit 5, and hopefully you will be able to watch this either at home or in class, and there will be a handout, Exploration 1-3, Introduction to Definite Integrals, for you to pick up. It's also on Edline, as is this PowerPoint, and you can work through this together or before you come in. I also do have a calculator program that I'll transfer to you, but obviously since I'm not there, I can't do that. But at the end of this PowerPoint will be a slide with a link to a computer program that does the same thing that this calculator does. And the program is not necessary for you to get, so don't anybody sweat if you don't have the program, or it's just it's a nice visual to explain today's topic, or visualize it, I guess I should say, and then also it will help with your homework. This is the handout, and the hint that I will give you about this handout is to think about your turkey hand assignment and maybe chunk some of the boxes all together. Think about geometry. In the example 1, maybe think about a large rectangle that you could make before you start counting partial boxes, and in number 6, same kind of thing, right? Even though that's a almost a semicircle, think about a rectangle in the center of it before you start counting partial boxes. The most important hint, though, is to consider the units. That you have the vertical axis on the first graph is in feet per second, and the horizontal is in seconds. And in number 6, the vertical axis is area units, and the horizontal axis are just linear units. And then think about the math you're doing and what that would mean for your units. So Unit 5, the definite integral. That's what this unit is going to be on, and the definite integral means that you have a start and a stop. The picture here actually could not be a definite integral because of the asymptotic behavior there at 0. The area is not bounded. So for us in Unit 5, you are also always going to be considering a finite area. A start, a stop, a top, and a bottom. How we're going to calculate the definite integral in this unit is estimating with finite sums. Finite, and again, means that you have a certain number, and it is going to be a bunch of sums, and you're just going to add up a lot of products. In this unit and on AP, a lot of your point value is going to be in the setup, not in the final answer. So make sure that you are meticulous about showing an AP grader what you are summing up and what units you get out of that. So there are 2 halves of calculus, and we've already covered the first half, believe it or not. The derivative, which is rates of change, slope, rise over run. Now we're going to turn our attention to integral calculus. So as you recall, with derivatives, slope, and with integrals now, I want you to think area. Slope, y units compared to x units, y units over x units, y units divided by x units. The integral is going to be calculated area, and it is also involving y units and x units, but instead of being a ratio, it is a product. The definite integral of a positive function, and note that we are going to talk about a positive function for a while. That means the function always lies that we're considering always lies above the x-axis, and it will correspond to the area under that function. This definition will get more formal and will expand to cover all functions, but for right now, to cement the idea of area under a curve, we are just going to talk about functions that all lie above the x-axis. So the methods that we're going to use to estimate these finite sums, geometry, just like you did with the turkey, with your hand. So if you have an area and you can find a rectangle under it, a part of it is looks like a trapezoid, a circle, a triangle, any geometric shape or combination of geometric shapes. Calculate those geometric shapes and add them up, and then maybe add all your little partial ones that are off to the side. A little bit more formal method for this is only excuse me, using rectangles, and it is called the RAM method, and that's not me. I know I make up a lot of stuff, but RAM is an actual calculus term, and it means you chop up the definite area. So for instance, in this picture, 0 to 4, and you constantize the function over an interval. So as you can see, my first rectangle there has a height of 5, and the interval is a width of 0.8. So that first rectangle is, of course, an area that is 5 times 0.8, and the second rectangle is about 7 times 0.8, and the third rectangle, so on and so forth. Note that I don't obviously cover all my area. Sometimes my rectangle lies under the function, sometimes it lies on top of the function. Hint, that depends on the behavior of the function. Can you see that? But when I sum all those rectangles, I do get an approximation. Later we will learn a trapezoidal method. Note that in that picture, instead of constantizing the function over each interval, I linearize it. So you're just kind of faking. You're pretending that, oh, the function for RAM method, the function has a constant height over a certain interval, and for a trapezoidal method, the function has a linear height. So it does change over the interval, but at a constant rate. So, given a function, x squared plus 2 on the interval 1 to 5, so a nice algebra 1 parabola, let's approximate the area under that. So between the x-axis and the height of x squared plus 2 on the interval 1 to 5. Here's a screenshot of that function on 0 to 5, but remember I only care about the area from 1 to 5. So I have a choice here. They just said approximate it. So if I choose to use rectangles, and I can make my rectangles any width I want, and I can make as many rectangles as I want. They can be different widths or the same width. Here I'm going to use the LRAM method, which are both methods that I showed you on the last slide, and why it's called a left-hand rectangular approximation method, or LRAM, is because the height of the function I chose on each sum interval came from the left side of the rectangle. So notice here in this picture, the first rectangle I drew has a function height of f of 1. The second rectangle has a height of f of 2 and is 2 units long, and the third rectangle has a height of f of 4. Notice, not a very good estimate. Next time I did a little bit better because I made more rectangles. And this time my delta x was the same for each one. Right? So in this time I used f of 1, f of 2, f of 3, and f of 4 as the constant heights of the function for each interval. So that is just multiplying f of 1 times 1, f of 2 times 1, f of 3 times 1, f of 4 times 1, and adding all those up and saying that's an approximation of the area under the curve of x squared plus 2. Hopefully you can already see where this is leading, that in order to get the best approximation, I need to keep increasing the number of rectangles. So I can write this area approximation all fancy, but note that it is just a product of function heights and widths, and those widths are along the x-axis. That's why you see that delta x there. And f of x sub I just means different function heights, and then of course that capital sigma just means add them all up. So you pull this notation out at parties, you look very, very smart. It is just an approximation, of course. This time I'm going to give you a function, same kind of algebra 1 parabola, 1/8 t squared plus 1, but I'm going to attach units to it. I'm going to say that the velocity in meters per second is represented by this function v, and I want you to use LRAM sub 4, or LRAM 4, to approximate the distance the particle travels over the first 4 seconds. So note this is the first time I've used that subscript. That subscript tells you two things, really. Duh, 4 means how many rectangles I want you to make. But also this notation is traditionally used to indicate that the subintervals are equal. So I'm going to take my first 4 seconds, 0 to 4, and say I want 4 rectangles, so that would be each rectangle would, shocker, have a width of 1. There is a formula for that, right? B minus A, which is your right endpoint minus your left endpoint divided by n, the number of rectangles you want, will give you your width. So here is my function, 1/8 t squared plus 1. Notice the first thing I do is mark the heights of my rectangles. And since it's LRAM, it is the left endpoint. So notice I'll be using v of 0, v of 1, v of 2, v of 3. v of 4 does not get to come to the LRAM party. Draw my rectangles. The behavior of the function, which again I'm leaving up to you to see if you can figure out which behavior, means that this LRAM will be an underestimate, as you can clearly see by the missing area. I calculate my velocity values at 0, 1, 2, and 3. And again, for AP, this is the part they need to see. They need to see the setup. They need to see that you are multiplying appropriate function heights times whatever your delta t in this case is, or the width of your rectangles. If the width of your rectangles is constant, as it is in this case, you could factor that out front if you like, and just add your function values and then multiply by, in this case, 1. Notice I say that LRAM 4 is exactly equal to 5.75, but that approximate the distance. You've got to make it clear as how you freaking get distance out of adding a bunch of areas of rectangles. That's where the unit discussion comes in. If your y units are meters per second, but your time is in seconds, and you're multiplying meters per second times seconds, the seconds will cancel out, and that's how you get distance, 5.75. Again, this is an underestimate. Just because I have chosen to use the left-hand rectangular method for the previous examples doesn't mean there aren't others. If there's a left hand, there's got to be a right hand. So note in these two examples that this is our same velocity function, that when I use the right endpoint to make the height of each rectangle, because of the behavior of the function, the rectangles are above the function. So this estimate will be too high. But you can see it is the same concept, right? I am making the function, pretending that the function is constant over the time 0 to 1, and then a different constant value over the from 1 second to 2 seconds, 2 seconds to 3 seconds, and then 3 seconds to 4 seconds. So the heights this time are v of 1, v of 2, v of 3, v of 4. Who got left out this time? v of 0 did not get to come to the RRAM party. Now, you might not have known that if there's a left hand and a right hand, there is going to be a midpoint rectangular approximation method. So the midpoint means that you have to be able to have a function where you can actually calculate the height at the midpoint, and that's going to be important in our next lesson. So here is a picture of MRAM 4, and again that 4 generally means that the subintervals are of equal width. So if I had the width is 1, this time the function height comes from not the left endpoint v of 0 or the right endpoint v of 1, but of v of 0.5, and then subsequently v of 1.5 and v of 2.5 and v of 3.5. But I am still same constant, pretending that the function is at a constant height over each one of those seconds intervals. So here we're going to actually calculate RRAM 4 for that same function. So I'd firstly draw my heights, starting again at v of 1. sketch in my rectangles, not shocked that they're over the function. Get my function heights at each one, at T1, T2, T3, T4. For AP, they're going to want to see this setup, that your distance is approximately RRAM. RRAM is exactly the sum of those function heights times the widths of the rectangles. Since my widths are the same throughout the whole problem, you could factor that out, and this time I get 7.75 meters. Making clear that I get meters because my Y units were meters per seconds and my horizontal units were seconds. And if you multiply meters over seconds by seconds, you get meters, distance. This time we will try NRAM. Same number of rectangles, but notice that my height comes from the center of each interval. I draw my rectangles at that height, get my velocity values at each one of those corresponding t values. Yes, I had a calculator to get those. And I cheated this time and didn't show my setup. I would lose points on my test or on an AP problem. Actually, there are many rubrics for AP that don't even have a point for the answer, and it's all in the setup. I mean, you are just calculating areas of rectangles and add them up, so it is the setup, the concept that they're testing. Notice this time I got 6.625. Do you think this is an overestimate or an underestimate? Can you figure out? Now I can kind of see from the picture, but again, it is a certain function behavior that will guarantee that. So what's different now? Same function, same units. I am still using MRAM, but notice my subscript is now 8. So this time I have to calculate b minus a, b being the right endpoint, a being the left endpoint of the entire interval, not of each rectangle. So 4 minus 0 divided by 8, not too difficult. And those are my heights of the rectangle. Drawing my rectangle, and hopefully as you can see this drawing, by seeing this drawing, that I am getting better. The area that now you can still see I have not covered is a smaller area than when I only had 4 rectangles by either LRAM, RRAM, or MRAM4. But the procedure doesn't change, it just means I have to write out a lot more, right? I have to write out 8 products. I just summed, this time I summed all the velocities. And can you see how I factored out delta t this time? Since I have a standardized width of a half, I factored that out of the summation and then just multiplied times all my function values. Again, this would not make AP happy. They're going to want to see your setup of all of your values. And you can even just use function notation. You don't have to write out that 1.00781, 1.07031, blah, blah, blah. You can literally just write v of point, v of a fourth, v of 3/4, v of 5/4, so on and so forth. Now I used all the decimal places I got here, 6.65624 meters. Again, notice that I have units on my answer to highlight that I get pretty close because I've increased the number of rectangles. It's pretty good. The actual value is 6.666666 meters. Hopefully you're seeing where I'm going with this. How do we get the exact value of the area under a curve? Well, certainly there's the algebraic way, which, just like with derivatives, we learned how to approximate before we ever learned how to find the exact slope of a curve at any point. But this isn't just because they're trying to torture you early. In order to find the exact derivative or the exact area under a curve, I need to know the function. Well, what if I don't have an algebraic expression for the function? Or what if it's just heinous? It's so awful, and maybe just an approximation is all I need. As long as my approximation is decent enough and I can figure out my error, then the approximation might be the more efficient way to handle the problem. So that's why you're going to be taught and tested on estimating even after you know how to find the exact area under the curve. But of course, the whole idea is increasing the number of subintervals, the number of rectangles, get you closer and closer. So just like derivatives, who has limits at the heart of derivatives, limits is also at the heart of integrals. So the exact area, not an approximation, the exact area is the limit as the number of rectangles or subintervals goes off to infinity of a sum of a bunch of products, function heights times intervals along the x or horizontal axis. Crazy! Here's an applet showing how when you start with 2 rectangles, increase to 3, to 4, to keep going and keep going. Hopefully you can see here that the area under this curve, as the number of rectangles increases, gets better and better and better. And if you can go off to infinity, which limits let us do, you will get the exact area. I also chose a function that has different behaviors, again hinting towards seeing if you can figure out when I have an overestimate versus an underestimate based upon the behavior of the function. So this slide takes you through the steps of the program that you will get linked to your calculator. Again, if you want to have it for today, I will be there at lunch or after school, and anybody from Mr. Chase's or Mr. Davis's class also will have gotten this during their class, and also 5th period, because I'm only going to be gone for 3rd period. But on the next slide, I have a web address or a link to a computer program that does the same thing. So I found this, as some of you know this website already. I've heard some of you talk about it. It's a really nice one, especially for visualizations. So this one, I put some arrows here next to the window where I had to input information. So hopefully you can see I inputted our velocity function, 1/8 x squared plus 1. I changed as x goes from, and I put in 0 to 4 using the first number of rectangles that I did, which was 4. And then you can see why there's a pull down window where I can take samples from the left to do LRAM, RRAM, or MRAM, and it will give you the approximation based on that. And it also tells you the exact area. So again, you can start to think and play around with when do you get underestimates and when do you get overestimates. So the homework from the first slide, of course I'm not checking on Tuesday or Wednesday because that's your unit test for Unit 4. You have your review sheet and your QR code to the solutions. So I will be checking this homework on Thursday. See ya!